Okay, let's start. So we were looking at reductions. And so what are reductions? Let's say we have some hard problem to solve. Then you reduce it to some problem which you already know how to solve or which is easy to solve. And we saw quite a few reductions this way. So we want to transform the input of one problem to the other problem which we want to reduce, such that if we can solve that problem, we can get the solution to the original hard problem. Okay. There are many ways to achieve this kind of transformations, but we need this additional condition that the solution to the reduced problem should give the solution to the original. Okay. And we saw a few reductions, and we were looking at this example that satisfiability, Boolean satisfiability. So you are given some formula in conjunctive normal form. So this kind of representation where we are taking uh, and over ors of certain variables, this is called a conjunctive normal form. There is another thing called disjunctive normal form, but that we are not interested. That is just or of ands of variables. Okay. So here's one input. We saw how to reduce it to just 3 variables per clause. So initially, the satisfiability problem, it could have any number of clauses and any number of variables inside each clause. But now we want to reduce it to just 3 variables per clause. Okay. So here, first thing has only one variable, second has 3, third has 2, and fourth has 4 variables. Okay. So we decided to reduce it in this way. When there is only one variable, we introduce 2 additional variables and consider all possible combinations of these 2 variables. Right? So x got reduced to x or a or b, x or a or b bar, x or a bar or b, and x or a bar or b. Okay. So if these 4 can be satisfied in some way, then x must be true. Right? So you cannot have x false and some truth assignments to a and b. Let's say I said x false, a true, and b false. Okay. Then this particular thing will not be satisfied, right? Because x is false, so a is true, so a bar will be false and b is also false. So this thing will be false, and therefore the original our reduced formula, that entire thing will also be false. Okay. And similarly, if the original thing was false, then no matter what we set a and b, this thing also will be false. Right? So if x is false, then this formula is also false, always. It doesn't matter what you set a and b, one of these clauses will always be false and the entire formula will be false. Okay. So the same thing we can do for here we had only three variables, x or y or z, so we didn't need to do anything. X or z bar, there are two variables, so we can introduce one additional variable L and write this as x or z bar or L and x or z bar or L bar. Right? Similarly, we can do things for four variables. Okay? So one or two were easy, four is slightly more difficult, but let's just verify this as well. Okay? So initially we had y or x bar or w or u. Now we reduce it to this formula where we introduce additional variable m. So y or x bar or m and m bar or w or u. Okay. So if the original formula was true, right, then we can find the true assignment for this formula. Okay. So when can this particular thing be true? Either one of these y, x bar, w or u is true. Okay. If y or x bar is true, then I can just set m to be true and this entire thing will be true. Okay. On the other hand, if w or u are true, then I can set m to be false so that m bar will be. And similarly, if the original formula was false, then no matter what I set m, this formula will always be false. Okay. So when is this false? When y is false, x is false, that means x is true, w is false, and u is also false. Then one of these things, m or m bar, has to be false. Either m is false or m bar is false. In either of the cases, one of these formulas will always be false. Therefore, this particular formula will always. Okay, and we saw one more example which had 6 variables in it. And how do we reduce it? That introduced all these new variables L1, L2, L3. Yeah, so we reduced it to 4 clauses, each containing 3 variables. Again, you just apply the same logic. When there are 6 things, you introduce these 3 new variables L1, L2, and L3, and take the first 2 variables and merge it with the first new variable. Okay. And then take its complement or W bar or L2, L2 bar or Z bar or L3, L3 bar or U or V. Okay. And again, as we did, if this original formula is true, then there is some truth assignment to this formula such that it will also be true. On the other hand, if this formula is false, then no matter what you set L1, L2, L3, the combination of these 4 things will always be false. Okay. So any questions so far? Okay, let's move on. So this was an example of SAT reducing to 3 SAT. We are given the original formula and we reduced it to 3 variables per clause. But reductions come in different types. So it doesn't need that if you are given a logic-based problem, you have to reduce it to another logic-based problem. So this 3 SAT is actually a universal kind of formula. So almost any kind of algorithmic problem you have, you can always find some logical interpretation for that. And you can formulate it as a 3 SAT formula. always, whichever problem. In fact, this was the first classical NP complete language, right? So any hard problem you have, you can always reduce it to 3 sat, and that is why reduction to 3 sat is very important. Okay? So we should be able to know how to reduce it to some satisfiability problem. So what this says is that if you can find an efficient solution for 3 sat, you can solve almost any hard problem in computer science in polynomial time. Okay. So let's see how to formulate other problems. Uh, so let's look at some graph theoretic problem and how it reduces to satisfiability. By the reduction we just mentioned, you can further reduce it to 3 sat. Okay. So what's this 3-color problem? So you are given a graph, a set of vertices, a set of edges, and you want to color the vertices using 3 colors. Let's say red, green, or blue. Okay. What you want is if 2 vertices share an edge, they should not get the same color. Okay. And every vertex should receive exactly 1 color. Okay. So there are many these online coloring games, and you can try to search online, and they're very interesting. But in general, it's very hard to color any graph using only 3 colors. So, for instance, if you look at, let's say you have some map of India, try to color it using 3 colors, okay, such that no two neighboring states, they get the same color. Okay. That is also a slightly hard problem. You can try to look at it. And in fact, any graph theoretic problem will have some logic interpretation always satisfied. Okay. So, how are we going to model this 3-color problem using a SAT formula, a Boolean formula? Okay, so the task is really simple, is that whatever constraints you have, you write it as some satisfiability condition, some formula, Boolean formula. So how are we going to write it? Okay. Let's say we are given as input this graph A, B, C, D. It could have n number of vertices and m number of edges. But just for simplicity, for showing an example, I'll consider a graph with just 4 vertices, A, B, C. How this formula looks like. Okay. So what was our first constraint? Is that every vertex should receive exactly 1 color. Okay. So how are we going to write this? Is that we introduce these variables AR, AG, AB. Such that AR means that A is colored red, AG means A is colored green, and AB means A is colored blue. Okay. So we want that every vertex should receive exactly 1 color. So I'll just show you how you'll model this for vertex A. Right. So this first constraint is AR and AG bar and AB bar. That means that if AR is true, then AG and AB have to be false. Right. So if A is colored red, you cannot color it with green or blue. Similarly, if A is colored green, you cannot color it with red or blue. And if A is blue, then you cannot color it with red or blue. Okay. So this is one clause which we have for the vertex A. Okay. Similarly, you can do for B, C, and D. So you have, if you have n vertices initially, you have these n clauses, which will denote that every vertex receives exactly 1 color. Right? And what was our second constraint? That no two neighboring vertices receive the same color. Okay. So the constraint here will be AR and A is edges with B. So you are given the edges initially. that means B R bar, right? So if A is colored red and A is neighboring with B, then you cannot color B with red. Okay. So similarly, you can write it for other edges also. Okay. So there are m number of edges, and every edge will have two such clauses. One is that AR and AEB will imply BR bar, right? Other is BR and AEB will be AR bar. You repeat it for all possible colors. Okay, so there are three many colors, and corresponding to each color, we'll have two such clauses. Okay. So don't worry about this implies thing, because if A implies B, you can write it as not A or B. Okay. So this is a standard theorem in logic, and it's very easy to verify. Okay. So what we have is, for every vertex, you have these three clauses. So what's the total number of clauses? That is 3 times n, if n is the total number of vertices here. And for every color, you have two clauses corresponding to every edge. There are three many colors, so there are totally 6 clauses corresponding to every edge. So if there are m many edges, you will have totally 6n. And here we had 3n. So 3n plus 6n many such clauses we have. So it's just a polynomial number of clauses, and hence it is a polynomial time reduction. Okay. So if you want to have more practice in this kind of stuff, pick any graph theoretic or whatever, geometric problem or graph theoretic, and you can always model these constraints as a satisfiability formula, and that is why this is right of the universal language which we can model this formula. Okay. The other direction is more complicated, but that we will see later. Okay. How does SAT reduce frequency? Okay. Okay. So now we will see some harder examples, which are kind of easier. And now we want to consider two SAT. Okay. So we want to reduce it to some graph theoretic problem now, strongly connected components. Okay. So let me just go back to our original example. Okay. So for instance, let's say we had this formula, x or y bar or w bar or z bar or u or v. Okay. And we reduced it to 3 variables per clause. Now if I ask you 2 variables per clause, okay, then it is very difficult to do that. Because you might be able to do something like x or L1 and L1 bar or y bar. But then it's the final formula which you will get, it won't satisfy the desired condition that if this formula is true, you can always make the resulting formula true. Okay. So one natural question here is, why we reduce it to 3 SAT? Why not 2 SAT or 1 SAT? So those problems are in fact very easy to solve, and this SAT problem is what we consider very hard. Okay. So 2 SAT is in fact a very easy problem, and we will see why it is easy. Okay. So what we have here is that okay. So let's say we have this formula where you have these 2 variables per clause, and we want to reduce it to strongly connected components. Okay. So what are these strongly connected components? Let's say you are given some directed graph, so there is direction on edges, and you want to find components or subgraphs such that for every two vertices, there is a path from U to V, as well as there is a path from V to U. Okay. So what we want here is that you are given this two set formula where there are just two variables per clause. You have to construct a directed graph such that if you can find the strongly connected components in this graph, then you can solve this two set instance. Okay. And you might know that you can solve the strongly connected components using some depth first search. Okay. But right now we are not interested in how to solve strongly connected components in polynomial time. We are just interested in given a two set instance like this, x or u and u bar or y or x bar or y bar. I want to construct a graph such that if this formula is satisfiable, if such that if I can find some strongly connected components in this graph, you can solve this formulas. Okay, yeah. So tell me how you will reduce it to this problem. Yeah, there is some question, I think. What is the purpose behind reducing the number of variables in each clause to 3 in the set? So we would expect normally that the larger the number of variables, the more difficult every set instance gets. So it is an interesting thing that you would like to reduce it to the as small number of variables as possible. Okay, so in that sense, it is interesting, and that is why we reduced it to 3 sets. Okay. But yeah, in general, whenever we want to reduce to something, we normally reduce it to a sat instance, and then you can see that it also reduces to 3 sat. Okay. So for instance, in this case, we saw that we can reduce it to 3 variables per clause, but can you reduce it to 2? And that is difficult in general. Okay. Uh, we don't know how to reduce it to sat. So in fact, we will show that this problem is in fact easy. 2 sat in polynomial time reduces to strongly connected. Okay. So how should we do this reduction? From 2 sat instance, I have this formula given to you. X or u, u bar or y, x bar or y bar. I want to construct some graph. So what do you suggest? Okay, so let's see how to solve this problem. So we are given the constraints, its clauses, and x or u, and u bar or y, and x bar or y bar. Okay. So then let's construct a graph where we have x bar, u bar, y bar. Okay. So we draw this directed graph with vertices exactly these variables and their complemented versions. Okay. And the main challenge is how we will construct the edges. Right? It has to model the constraints of this SAT formula in some way. Okay. So what we look at here is that, let's say if x is false, then u has to be true for this formula to be satisfied, right? So if x is false, then u bar is also false. Similarly, if u is false, then x bar is also false. So you draw an edge from u to x bar. Okay. Then if u bar is false, then y bar is also false, right? So that this thing will be true. Okay, this thing will be false. Okay? No, this thing will be true in that case because if u bar is false and y bar is also false, that means y is true. Therefore, this thing will be satisfied. Okay. Similarly, you can do the other way. If y is false, then u is also false. U will have to be set to false. Then finally, if x bar is false, then y is also false. Then this thing will be true. And if y bar is false, then x will also have to be false. Okay. So these are the set of edges. These are the set of vertices which we have. And now what can we say looking at this directed graph? Okay. Now looking at this directed graph, we want to find a satisfying assignment for the initial clause. Right? So how are we going to do that? Yeah, tell me. You are given this graph now, directed graph with these vertices and these edges. And looking at these edges, you want to give me a satisfying assignment for this particular formula. Yeah, we have an answer, which is h from x to u. That means x or u bar. Uh, no, h from x to u implies that if x is false, then u will have to be set to false. Yeah, exactly the same. Yeah. So what we are doing with these edges is that if x is false, then u bar will have to be false to satisfy this particular sum, right? So the idea is essentially this, that you follow the edges to form some path, okay, until you reach the original vertex x. So in this case, there is a path from x to u bar, then u bar to y bar, and then y bar to x. Okay. So this is a strongly connected graph. Correct. So for any two vertices, you can find the path from one vertex to another. Okay. And once you find this strongly connected component, which is x, u bar, then y bar, you set all of these variables to false. Okay. So we'll set x to false, u bar to false, that means u is true, and y bar will also be false, that means y is true. Okay. So x is false and u and y are true. And if you look at this original formula, y is true, that means this thing will be satisfied. U is true, that means this thing will be satisfied. And x is false, that means x bar is true. So this thing also will get satisfied. Okay. So once you can find the strongly connected components here, you can solve this original two-side instance. Okay. And if no such strongly connected component exists, that means this original formula was false. You cannot find a satisfying assignment to this. Okay. So these are very interesting, the SAT-based reductions, because almost every industrial problem works via this way, that they reduce it to some SAT problem, and then they have these tools which can solve some special cases of satisfiability. And almost all practical instances, these satisfiability instances are easy. Okay. Even though theoretically it's a difficult problem, satisfiability. How do you satisfy all these constraints simultaneously? But most of the practical instances, they are very much solvable. And so this is the general approach, that if you are given some formula, we try to model it as a SAT-based instance. Okay? And then you try to apply some SAT solver to solve it. Okay. Okay. So let's look at a few more reductions. So here we set x, y bar, and u bar to be false because there was a path from x to u bar to y bar, and y bar to x. If there was a path from y bar to x bar, then this thing would have been false because then there is no strongly connected component. Okay. So let's look at some more reductions. So this is another easy one. This segment intersection reduces to independence. So what do I have this problem? Segment intersection. Okay. So you are given a bunch of line segments. There are n many line segments. And how they are given is that you are given the x and y coordinates of its endpoints. Okay. And you want to find the maximum number of non-intersecting segments. You want to find the maximum number of non-intersecting segments. Okay. In fact, this is a good exercise in the dynamic programming. You can try to apply dynamic programming to solve this particular problem. But here we are not interested in solving this problem. We want to give a polynomial time reduction to independent set. Right? So you all know what the independent set is. Maximum independent set is given a graph. You want to find the maximum size of a subset such that no two vertices in S share an edge. Okay. Now we are given this instance of segment intersection and we want to reduce it to independent set. So you are given this line segment, you are given this x and y coordinates. I want to construct some such that if I can find the maximum independent set in this graph, I can decide the maximum number of non-intersecting segments. So how can I do this reduction? So from these coordinates, x, y coordinates of the endpoints, I want to construct some graph. So how do I construct this graph? So I take this graph whose vertices denote these segments. Okay? And there is an edge between two vertices if and only if the corresponding segments intersect. Okay. Uh, so this is a geometric problem. You know when two segments intersect, right? Yeah. So there is one answer. We can let a vertex denote a line and vertex V1 is connected to vertex V2 if and only if the line V1 intersects V2. Yeah, exactly the same thing. Uh, and you know how to decide whether two corresponding segments intersect, right? Because once you have the two endpoints corresponding to one segment, you will just check whether the two endpoints lie on opposite side of this particular segment. You can apply some cross product thing and can verify that easily. Okay. Yeah, so this is a good reduction to know, but this is a bad way to solve this problem. Okay, because maximum independent set is a very hard problem in general, and segment intersection you can solve in polynomial time using dynamic programming. So it is a good exercise. Try to apply dynamic programming to solve this segment intersection problem. Okay. Yeah, let's see some more reductions. So another example of reductions is we are given this traveling salesman problem. Okay. Given a list of cities. Okay. So there is some salesman, he has to travel from city to city, and you are given the distances between each pair of cities. Okay. And the question is, what is the shortest possible route that visits each city exactly once and returns back to the origin city? Okay. And then we have another problem, which is this Hamiltonian circuit problem. And this question is, does the given directed graph contain a path which begins and ends at the same vertex, such that each vertex is visited exactly once? Okay. So you can think of this thing as a generalized version. Traveling salesman is a generalized version to Hamiltonian circuit. Okay. And what we want to show here is that Hamiltonian circuit problem reduces in polynomial time to the traveling salesman. Right? So if you can solve this traveling salesman problem, then you can also solve Hamiltonian circuit. Okay. So basically they are the same problem, but here we are given the distances. So the edges will have some weights. Okay. And you want to find the shortest possible. Okay. So what edge weights will you give so that you can solve this Hamiltonian circuit problem? So the natural thing is we set all these edge weights to 1. So the distance between each pair of cities is 1. And we want to find the shortest possible route of length n because there are n many cities here. Right? So that's exactly the idea. And if you can do this, just set the edge weights to 1, you can solve this Hamiltonian circuit problem. It's just the same problem written in two different languages. Okay? Here we have cities, here we have vertex. Okay, so this is another fairly straightforward reduction. Let's see some more examples. Now I want to introduce to you this dominating set problem, which is, what is the dominating set for a graph? It is a subset D of vertices such that every vertex not in D is adjacent to at least one member of D. Okay. And what we want is, we want to reduce vertex cover to dominating set. So I want to show that if I can solve dominating set on the graph, then I can also solve vertex cover. So let's take this example, A, B, B, C. So these are the edges. I'm defining a graph on these vertices. The vertices are A, B, C, D, E, F, G, H. Okay, and these are the edges which I have. Right? So there is an edge from A to B, B to C, A to C, and so on. These are the edges which I have. And I want some kind of reduction. Okay? From this, I construct some other graph such that if I can solve dominating set on that graph, I can solve vertex cover on this. So let's say I want to ask the question, is there a vertex cover of size at most 5 in this graph? Okay. I'm not interested in solving this problem. I just want to reduce it to this dominating set. Okay. So what's the dominating set for this particular graph? You could pick A, B, and E, and F, and G. Okay. So if I pick A, B, E, F, and G, okay, then that is a dominating set. Or can I get a smaller one? So for instance, I could pick D, F, G, and E. No, okay. So we have some kind of dominating set, and we want to reduce it to vertex cover. So let's say I want to find the vertex cover in this graph. When am I sure that a dominating set for this another graph will solve the vertex cover on the original graph? So what is the new graph that I must produce? The first thing to notice here is that if you take the same graph, that is not going to work always, right? So for instance, you could take a triangle. Okay, let's say I have just these first three edges, A, B, B, C, and AC. Okay. Then C covers A and C covers B. So all vertices are covered. So every vertex not in D is adjacent to at least one member of D. So just the vertex C is a dominating set. But if I want to solve vertex cover, then I have to pick two of these edges, two of these vertices. A and B. Right? Only then all the edges will be covered. Okay? So you can look at vertex cover as vertices covering edges, and dominating set is vertices covering vertices. So in general, the dominating set could be different from a vertex cover. That very different. So the same graph doesn't work. So what other transformations I can make to this graph so that if I find the dominating set on that graph, I'll also be able to solve vertex cover. Okay, this is a slightly more difficult reduction. Uh, yeah, let's see how to do it. So we can draw a parallel edge between every two neighboring vertices. So initially there was only one edge between these vertices, let's say A to B. We draw another parallel edge, and on the original edge, we place a new node on every edge. Okay. So let's say I have a new vertex AB, which I place on the edge from A to B. You draw a parallel edge from A to B. Okay. And it turns out that if you can solve the dominating set on the resulting graph, then you can solve vertex cover also on the original. So what's the point of constructing this parallel edge is that for every new node, if you place a new node on every edge, let's say I had placed a node AB on this edge from A to B, then I can't pick AB on my uh, dominating set, because otherwise this parallel edge from A to B that will remain uncovered. But here I am interested only in covering vertices to vertices, right? So if I include AB in my final dominating set, it will only be able to cover three vertices: A, B, A, and B. Right? Instead, if you pick A, for instance, then you can cover A, B as well as AB. Okay? And maybe some other vertices as well can cover C also. So we will formally show that if you can compute this dominating set in this graph, it will give you a vertex cover in the vertex. Okay? Because this is vertices covering edges, this is just vertex covering vertex. Okay, are there any questions? Yeah, there is a question. Dominating set for this graph is BF. Okay, let's check it out. But yeah, B is covering A, C, D, and E, and F is covering G and H. Yeah, that's so you can see that dominating set is in fact much smaller than the vertex cover, but you can construct some other graph which we define this way, and if you find a dominating set on that graph, you can solve the vertex cover, the original graph. Okay, one more question. What is referred to by placing a new node on every edge? Okay, so what I mean is, let's say I have some new node, let's say I. So instead of A, B, the graph will have two edges from A to I and I to B. Okay. Similarly, if I have this BC, then I introduce a new node J and I draw an edge from B to J and J to C. Okay, so if there are no more questions, we can continue this reduction in the next class. There's one more thing. No, there are not two edges because now we have broken up this edge. So we into AIB. So the original edge from AB does not exist anymore. Okay. So there is just one edge from B to C, uh, but the original edge has been broken as B to J and J to C. Okay. See you on Thursday and stop this meeting now.